exceptions to the quantum mechanics electron configuration. Now there's two general exceptions. First exception, we'll actually have a look at a question to better depict this. Many of the transition elements here have more than one stable valence because of their electron configuration. Let's look at lead, and we'll do lead as the atom as well as its corresponding ions with a 2+ charge and a 4+ charge. So let's look at lead first. Again, this here is going to be the atom, and we're just going to get the electron configuration for all of this. Remember, this was our rule: 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, and then our 6 is up there. All in this order. If you haven't memorized this by now, please do so. Now let's get our lead. And we know that lead is quite large in terms of its atomic number. So let's do this all together. Believe it should go all the way up to, I think, very, very close to the 6s's or the 6p's. So let's try it. We're going to start all the way down here. So we got our 1s's, our 2s's, our 2p's, 3s, 3p's. Remember, got to jump up to the 4s, then back to the 3d. 3d's, and then after that our 4p's, and then our 5s's, and then from here the 5s goes all the way up to the 4d, and then it goes to our 5p's, after the 5p's goes up to the 6s, then a 4f, which would be all the way up here on the side. Oops. And then we go to our 5Ds. Let's see if this is enough. If we need to go to a 5D. Yeah, if we need to go to a 6P, we'll see if we need to go there. So let's write it out. I guess our lead here is an 82. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80. Okay, so we're at 80 right now here, but I forgot to write it out. This was the 4F, and this here was the 5D. So we're at 80 here. We just need 2 more. So actually we do need to get to the 6S. So let's go to the, sorry, not the 6S. We've finished the 5D. So we got to go to the 6P. So the 6P would be right here. So we got 2 more over there. So this here is our electron configuration. I know this was definitely a long one, but you got to do what you got to do. So now we got to figure out what is our electron configuration. Well, I mean, you can write it all out, but let's actually just do the shorthand form. The shorthand form would be a lot easier in this case. So we need to do our, before we do our 2 plus and our 4 plus, let's do the shorthand configuration. Actually, no, the question just say full and short. So you know what, let's just do the full and short one. So let's write it out. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Then we got to go to our 3 d10s. After that, you got our 4p's. So 4p is a 4p6. And then our 5s's is a 5s2. After the 5s2, it goes to a 4d. So that's another 4d10. After that, we got our 5p. So that's a 5p6. After the 5p6, we got a 6s2. After the 6s2, we got a 4f. That would be a 4f14. And after the 4f14, we got a 5d, so that'll be a 5d10. After the 5d10, we got the 6s2s. After the 6s2s, we got the 4f14s. Sorry, hold on. 6s2, 4f, 5p, hold on. Give me a second here, y'all. 5p6, and then we got the 6s2s, 4f14s, then the 5d10s. Okay, then we got to go to the 6p's. We got to go to the 6p's. The 6p's is the 2. Alright, just want to make sure I didn't make any mistakes here. 6s, then the 4f's, then the 5d's, and then the 6p's. Yep, seems pretty good to me. So this here is our electron configuration, full hand. Now we can do the same one here, and we can do the shorthand version of this. So the shorthand version here is just going to go to our most recent noble gas. Our most recent noble gas before the lead would be the xenon. Okay, so if you look for a xenon on the periodic table, all right, so again, we're at lead over here, and we're trying to find the most recent noble gas. That would be xenon over here. All right, and as we can see, the period numbers here, we have 1, we have 2, we have 3, we have 4, we have 5. So it'll be in the 5p's. So here we got 1, 2, 3, 4, 5, 6. So our xenons would have to be ending off with a 5p6. So let's find a 5p6. 5p6 is right over here. Okay, so the 5p6 is finished. Right over here is our cutoff point. This is a fast way for you to do this without even having to count the number of electrons, because that would just be extremely annoying. So we're just going to do it faster that way. If you're confused as to how I was able to determine the p subshells that quickly on the periodic table, you would have to see the previous video on the electron configuration. So all of this has been finished. So all of this can be taken into account as xenon. Everything else after that would be the leftover amount that we would need to write down. Now, instead of deciphering the periodic table like how I just did, you could also just look at the most highest principal quantum number that was introduced. As you can see, 7s are not here, so it's definitely not going to be a 7. So it would have to be the 6s. So where's the first time that you see a 6? It's right over there. Even if the F subshells come after it, and then a D subshells comes after that, and then you see a 6 again after, it is okay. As long as you see that first principal quantum number that is the highest, that is likely, well, not likely, 100% definitely going to be the starting point after you find your noble gas. So all of this, like I said, is going to be the xenon. So xenon here, I would write it in the bracket. All right. So let me erase this a little bit here. And then after the xenon, within the bracket, again, the bracket does not stand for concentration. When we get to equilibrium and molarity, then this would have to be changed. However, right now, in quantum mechanics, you would represent these brackets as just the shorthand electron configuration. Again, does not represent concentration. After that, let's write down the leftovers. So we got 6s2, 4f14, our 5d10s, and our 6p2s. So this here is our shorthand electron configuration. So we've done it for lead, which is our atom. But the question is also asking for its ion. All right, so its ion here is 2 plus and a 4 plus. So if I were to write it here, our Pb 2 plus, let's look at what it would look like. Let's have a look at the shorthand configuration here. So I'm going to just copy paste this here, Xe, and then we have our 6s2s, our 4f14s, our 5d10s, and our 6p2. If it has a 2 plus charge, it means that it lost 2 electrons, so we need to get rid of it. Well, we don't need to draw this all out again. I mean, we already have it here. So if we want to get rid of 2 electrons, because now we are more positively charged than before by 2, these 2 electrons need to be given off because they are the highest energy level. It is taxing on the element, so it wants to get rid of it. So once this is gone, you are just left with, let's get rid of this, get rid of this, get rid of the 6p2. So what is our final answer for this one? It would just be Xe, 6s2, 4f14, and 5d10. It's that simple. The problem, though, is when we get to our exception rule. We now have Pb4 plus. Let's copy paste what we did before right up here, and let's decipher this. So we have our 6s2, our 4f14, our 5d10s, and our 6p2s. We need to get rid of 4 electrons now. Well, the 2 electrons are going to be easy. We already did that. But now we have to do it another time. You would think that we would get rid of it here, our 5d10s. So then it would be 5d8. However, this is incorrect, because when we start removing electrons, they behave differently. And through rigorous testing, we've figured this out, and it does work. These next 2 electrons does not come off the 5d10, despite being a higher energy level. It would actually be coming off of the 6s2s, because we always want to remove electrons from the highest principal quantum number first. So we want to get rid of the 2 electrons here because there is a 6 in front of it. So we want to get rid of that. So our final answer here would be Xe, 4f14, and our 5d10. Again, why? Because of testing. In reality, even though it seems as if this 5d10 is higher of energy level than 6s2, it does not behave that way. Because it is a 6 in front, it is a lot easier and it is less taxing on the element to get rid of the 2 electrons from the highest principal quantum number. This is why I don't draw these subshells extremely varied. So I don't put this 3p a lot higher than this 3s. So I don't put this 3p like here. Or I don't put this 4d much higher than this 4p, because it's all actually quite negligible. Sure, when we do our off-bar principle, you can think of it that way as a standard procedure, just get a good mark, right? In reality, though, it does not behave like that. In reality, these are all separated by a very minuscule margin. However, during testing, when it loses these electrons, as it acts as a cation, because Lead here is a cation. If it loses the electrons, it feels as if it's a lot easier to get rid of it here from the first principal quantum number. All right, so now that's finished. So that's going to be our shorthand configuration for our PB4+. Now, I know the question does say draw the electron configuration for the full and the shorthand. I don't think I need to show you how to do the full hand for this. It's honestly the same procedure, so just for the sake of time, I'm not going to show that. Now let's look at our second exception rule. All right, let's have a look at chromium. If we look for chromium on the periodic table, it is number 24. Hence, it has 24 electrons. Let's draw this out as if we are not worried about the exception. Just pretty much drawing it out the way I taught in the previous video. 1s, 2s, 2p, 3s, 3p, 4s, 3d. Again, let's see if this is enough. Again, we need 24 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember, do not forget Hund's rule. So that's 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. There we go. So we have electrons almost half filling the 3D subshell. Now, this is where it gets a little bit tricky. If we were to write this out, as we normally do, it would be 1s2, 2s2, 2p6. It would be 3s2, 3p6, 4s2, and 3d4. This is actually incorrect. Because whenever you are dealing with a d orbital, by the way, this also applies to the f orbital as well, but that's not for the scope with the level that you're on, so we're not going to be looking at the f orbital exception. 3D is enough. And honestly, the f orbital is very, very, very seldom to actually study because a lot of those are extremely reactive and unstable, and a lot of those are man-made as well. Okay, let's have a look at the d orbitals only. So with the d orbital, these 4 electrons here need to be balanced. When I say balanced, I mean consistent for every single orbitals that exist. The thing is, right now it is so close to being stable. Now, not 100% stable, but quite stable. If you have no idea what I mean by that, about 100% stable versus quite stable, in my layman's terms, I would highly recommend you to watch, I think it was the electron affinity video or the ionization energy video, where I go a little bit more further into that. Okay, in order for this to be quite stable, it just needs one more electron. So what actually ends up happening is this electron here that we see on the 4s subshell, it's actually going to move and go into there. So now we all have positive half spins on the 3D subshell. And this electron here goes away. Because, like I said a few moments ago, it's very, very minuscule, the distance between the 4s subshell and the 3D subshell. Okay, I'm reiterating this again, how important this is. It is very, very insignificant in terms of the distance that separates them apart. So through rigorous testing, it seems as if whenever we get to a point like this, if it's favorable and it's very, very close to becoming consistent with this teeter-totter approach where it's completely balanced, even though it's only half filled, it's balanced in a way, it would easily take this electron and put it here. This is a lot more favorable of a condition. Even though this 4s here only has one less. Now you may be thinking, if this 4s only has one electron left, then wouldn't this be extremely unstable? Technically, you're correct. It would be extremely unstable. However, this 3D here has 5 orbitals. So this would be a lot more taxing if this area here was vacant. So if it has a greater number of orbitals, it may be a lot more favorable to completely balance that one out, because this one here has only 1 orbital, so it's technically quote-unquote not a big deal. This is what the testing says. So our complete answer, let's put an X here. Our complete answer here would be 1s2, 2s2, 2p6, 3s2, 3p6. It's not a 4s2, it's going to be a 4s1. And our 3d4 becomes a 3d5. All right, so this is how we do that. This is how we do it for chromium. Now, something very, very similar can be done for copper. Copper, I'm not going to draw it all out. Again, for the sake of time, there's no need. You should be able to draw this on your own. If I were to just show you what it looks like, copper has an AR within the bracket, and then it has a 4s2, and then it has a 3d4. You notice how it is quite similar. Okay, so that's impossible. It can't be a 4. Did I? No, that's impossible. Never mind. It has to be a 9. Yep, there we go. 3d9, right? Otherwise, it would be mirroring this, which wouldn't make sense. So this copper here has a 4s2 and a 3d10. So if I were to just draw you the actual 4s2 here and our 3d10, which is quite close to it, and I were to draw 1, 2, 3, 4, 5, 6, 7, 8, 9, you notice how this is the same thing. But now this is very, very close to being 100% stable. Not quite stable, but very, very stable. 100% stable. Because it just needs one more electron here to be added onto there. So this is a lot more favorable. So we would actually get rid of that one and add it here. So our shorthand electron configuration, instead of 4s2 3d9, it would actually become 4s1 3d10. These two are extremely similar. And honestly, it's not just chromium and copper that has this rule. I believe it is also molybdenum, gold, and silver. They also follow this. Molybdenum as well. So these are these two exceptions. I'm going to be showing you 2 more questions, and I want you to pause the video and try it yourself, and then see if you can get the answer. And I'll just post the answer immediately after. Alright, this here is your question. In green, question of the day. There's going to be 2 of them here. I want you to give these a try. First, try the electron configuration of bismuth, as well as its ion of 3 plus and 5 plus. Only just do the shorthand configuration. Alright, you don't have to do the full. So I'm expecting the bismuth atom, the ion of 3 plus, and the ion of 5 plus. After that, I want you to try the second rule for the exception for molybdenum. But this time, because it's just the actual MO, or molybdenum, I want you to try the full and the shorthand electron configuration. Again, please pause the video and give it a try right now. This here is the answer. Please comment below if you have any questions.